Hey everyone, I'm Ronen Botzer, and I'm a director of product at Aerospike. In June, I'm going to be starting my 7th year at Aerospike. Previously, I was a solutions architect, and before that, I was an engineer. I've been giving talks at meetups about Aerospike, mainly talking about data modeling, and I've written some blog posts, again, mostly focused on data modeling, and that's kind of how I got into this workshop. So let's go over our agenda. First point, Aerospike is a document database. The next thing is we're going to go over list and map fundamentals, the ordering of values, value comparisons, how you find intervals, and then the operations API. We're going to talk about document-oriented modeling using bins versus maps. We're going to go over operations on nested elements, which is a fairly new thing, a few releases back. We're going to talk about denormalized and normalized modeling techniques in Aerospike, and then we'll talk about how we query for documents. Aerospike is a row-oriented distributed database. There's a lot of similarities conceptually between Aerospike and a relational database. In a way, a lot more than, say, similarities between something like Aerospike and Redis. So let's go over some of the terms here. In Aerospike, a namespace is the top level kind of container, and it's similar to a database or a table space in a relational database. A set in Aerospike, which is optional, is similar to a table, except for that it doesn't really hold a schema. Okay. A record is similar to a row. In fact, all the objects that are stored in Aerospike are called records, but really this is a row-oriented database. Records will contain one or more bins, and bins are like a column. They hold a specific data type and they're named. A set really is less of a table than it is an optional label for a grouping of records. So if you're using it in an organized way, a user set would be where you put all your user objects, but really a set can have any type of record in it because there is no schema. A record's digest is the unique identifier in Aerospike of the record in a specific namespace. And the digest is part of the metadata about the record that is kept in the primary index. The primary index is similar to a primary key in a relational database, but whereas the primary key is optional in a relational database, you can have a table without a primary key and just always scan it. But in the case of Aerospike, the primary index is always there. Every record has a metadata entry in the primary index. And the primary index is over not a set, but actually the entire namespace. So all the records in the namespace are held in the same primary index. So the clients talk to the cluster through transactions, and a client could be an instance of the Python client or the Java client or Go. Okay, it's a piece of software that you instantiate in your application to talk to the cluster, the Aerospike cluster with. The client designates a record with a key, the record that the operation is going to happen on. And if the client is given the key tuple of namespace, set, and user key, which is sort of the way to uniquely identify any record in Aerospike, it will calculate the digest for you. Now you can directly pass it the digest. That is like more the canonical key, but for convenience, you get this, one shot where it does it for you. Now, transactions in Aerospike are atomic. They execute in order. There could be multiple operations and they'll execute in order, and these happen under a record lock. While this record is being held, for example, for a write, like a insert or an update, other records are not going to be able to do anything on the record, including reading it. So those queue up. So be aware that it is atomic. And bins that you're operating on will have any of the supported data types of Aerospike, which currently are integer, double, string, bytes, list, map, geospatial, and recently hyperloglog, which is actually implemented as a Hyperman hash. And each of these data types has its own API of operations, and we're going to go over those soon. The digest that we mentioned is a RIPE-MD 160 hashing of the set and user key pair of data. And so here's an example where we're passing the 3-tuple namespace set and user key. The client hashes those last two into a digest, and now it can send the operation at the record. The record, if you look at it, has two main components. There's metadata, which actually is first thing stored in the primary index, but also if your data on SSD, there will be a copy of this on disk as well. And it holds things like the void time, which is how we calculate the TTL, the last update time, which is again when the record was last written or updated, and then the generation, which is how many times was it updated. The bins, as you see here, we have, for example, 3 different bins. We have a bin called I, which has an integer value in it, a bin L, which has a list value in it, 2 elements, fish and tacos, and then an M, which is a map that has 2 elements in it, 2 key value pairs right now. Let's say the operation in this case will be 3 things all at once. First thing, we'll increment the integer bin I by 3. Then we'll append avocado to the list values in bin L, and then we'll add another pair of key values to the map in bin M. So Aerospike records really are actually documents. They're identified by a key, but they're not restricted to one value. So even though you can use Aerospike in a key value mode, and in the past people have, there's a lot of older use of Aerospike where people will just, take a blob that is like compressed protobuf and they'll store it in Aerospike and they'll just use get and put operations. Maybe they'll have a counter, like an integer bin, and do the increment atomic operation on it, but that's about it. So that's kind of like the old school way to use Aerospike. And that's similar to how you would use Redis, for example, or Memcache. Those are actual key value stores. But Aerospike has had bins and has had complex data types that can all be stored in the same record. And if you look at it this way, basically it is a document. Okay, the record object itself is a document with a map of bins. Okay, and complex data types such as list and map can nest other data types inside of them, as long as these are valid data types. So for example, we have a record where it has that 3-tuple that identifies it, the namespace set and the user key. So let's quickly go over list terms. Here's an example list. It's just an unordered or list of numbers, numeric values. The index is the starting at 0, the position of the element in the list. So the value at index 2, if you go 0, 1, 2, is 7. And the value at -2 is 26. -1 would be 11. The rank is the value order of the elements in the list. So if you basically ordered them by their value and then their position in that new ordering is the rank. So the lowest rank is, the lowest value has rank 0, the highest value has rank -1 in this case. So the value of the element with rank 1 is 3. You can see we have 1, 3, 4, 7, 9, 11, 26. So, rank 1 is 3, rank 2 is 4, rank -1 is clearly 26, and rank -2 is 11. We have the ability to actually set a type on the list, and it can be either unordered, which is the default, or ordered. And this is what it would look like on the server side if we changed the, from unordered to ordered. An unordered list maintains insertion order. Okay, as long as new elements are appended, all the other elements stay as they were. So, it's a very cheap, like big O of 1 operation to add an element either to the beginning or the end, but especially at the end. Removing and inserting elements, other then at the end, we'll shift the elements. Okay, that's clear so far. And in an ordered list, it maintains rank order all the time. So every time you add a new element, it'll resort itself. And you can't insert an element. That's an operation that's not allowed on an ordered list because it doesn't really mean anything. If you want to say, I want to insert something in index 3, well, in this case, the indexing is by rank. Now let's look at list ordering. What if you had a list with different elements in it of different data types? So the order, basically, the lowest order is nil, which is it's a singleton. It's not really a value that Aerospike uses. Aerospike doesn't need nulls. If there is no placeholders like you would need in a kind of like strict two-dimensional table that is in the relational model. Okay, you don't need something holding the space. A Boolean, again, that's a placeholder. That type does not exist right now. Then you have integer, string, list, map, bytes, double, JSON, and infinity, which is another singleton that is used for, you'll see next, in all kinds of operations to express order, especially in intervals and ranges. So elements of different types, again, are ordered by type. So if you look at it, if you have the ordered version of this list, they're going to snap into grouping by type. The range of elements between nil and 10 is going to be these integers, okay? Because nil is the leftmost. It's to the left of the integers, even though it's not explicitly there. 10, obviously is not going to go any farther to the right of 11 because when we are looking at where we would insert 10, it would be between 9 and 11. Okay, so when you say give me the range of elements between those, you can see how it's that sublist that is mentioned there, 1, 3, 4, 7, and 9. The range of elements between A and an empty list is going to be, in this case, A and C, because you can see how list is to the right of string. The smallest list possible is the empty list. So if you're looking at the range between A and empty list, it gives you A and C. And the range of elements between empty list and infinity, again, a singleton that is not really a value, but more like an ordering related thing, is the list that includes 25y and 1. Okay, so there's only one element really there because the empty list is to the left of all the list elements and to the right of all the string elements. And then infinity is basically the end. In an unordered list, getting elements by rank will still obey this ordering. It's just we'll do it just in time and it won't persist it. So this is an example of where you need to decide what is more efficient for your access pattern. So for example, unordered list, if you're doing a lot of appends, unordered lists are ideal. If you're doing a lot of reads, then the ordered lists are more optimized. You're paying on every time you add an element, but it's more optimized for reads, especially if you're doing things like these range reads. So it's going to give you exactly the same results, but it's going to do it with a less optimal runtime. What about list value comparisons? What if you have things that are a complex data type, like lists, and you have a list of lists, or a list of tuples in this case, that are represented as a list? Starting with Aerospike 431, the way list values are compared has changed slightly, but that's been the case for quite a while now. So first thing, we're going to compare the elements in order from index 0. So you look at the first at index 0 of two list elements and you're comparing them. Then you're looking at index 1, etc. That is the highest priority for ordering. The next thing is the list length. So like we said, a list with the tuple 1, 1 is going to be to the left of 1, 3, the tuple 1, 3, and the tuple 1, 2 is going to be to the left of 1, 2, 0, 1. Okay, so let's do a quick exercise where we're appending things in order. We're going to start with an empty list. It's an ordered list. And now we're going to append the tuple 1, 1. So you can see that first element shows up in there. Then we're going to append 1, 3. And like we said, it goes to the right of 1, 1 because we're comparing the 0 and then we're comparing the first the position 1, and 3 is bigger than 1. Next thing is we're going to append 1, 2, 0, 1, and you can see how that slots in the middle between those two. Because again, 1, 2 is less than 1, 3, and the length is the secondary criteria here. And then we're going to append 1, 2, and that goes to the left of 1, 2, 0, 1. And that's, you can see how it ends. So now let's talk about intervals. We have an unordered list of tuples. These are all pairs of list values. And the interval operation is going to just in time sort this ordered list before it needs to do the operation, but it won't persist it. So when we actually do a transaction on this unordered list, it's going to be, depending on what we're trying to do, but if it's an operation that requires understanding of, for example, ranges, it would need to know what the order is. So this is what it's going to look like. That's actually like what you should be referring to about this. So 2 and nil. Okay, if we have the tuple 2, nil, it's going to be to the right of anything that starts with 1, regardless of the element count. Okay, so you can see how 2, nil is going to be to the right of 1, 2, but to the left of 2, 5. So, and the interval between 1, nil and 2, nil is going to be basically 1, 1 and 1, 2. 1 infinity is going to be to the right of any tuple 1, 2, 1 comma anything, and to the left of 2 comma anything. So, and you can see that it basically gives the same result. Now, one of them is, inclusive exclusive, and the second one is inclusive inclusive. This is the list operations API. You can see that it's grouped into 3 groups. One of them is write operations. They change the nature of the list. You have append and append items. The difference, one is just singular, the other allows you to add multiple items at once. At the end, insert and insert items allow you to insert 1 or more items into a specific index, like in between or before things. Set allows you to change the value of one element at a specific index, and increment allows you to increment an integer at a specific index. Sort, clear, and size also pretty self-explanatory. The get operations, let's just go over them really quickly. Get by index and get by index range. Again, we talked about what an index is, just a position. Get by rank and by rank range. You know what the rank is if you think about it in terms of ordering them by value, and then those are the indexes. Get by value interval, and get all by value, and then get by value list, where you ask for several values and get those out if they exist, and then get by relative rank range, which we're going to talk about that. And then there's the remove equivalence of those. Now, this list is actually like generic method names. The clients themselves have different names that might be a little different, but all these operations are implemented in all of the clients. So let's talk about an example where we're modeling IoT sensors, incoming temperature, using these list tuples. So what we can do is basically describe tuples. We have a situation where a sensor is taking a reading every minute, and every minute it basically logs a temperature. So these minutes since epoch, and this is just a cheap way to reduce the size of the integer. You just decide, a point in time where you're going to count minutes up from. And Aerospike, by the way, uses message pack for serialization, which anyway will kind of use smaller kinds of ints in order to represent smaller numbers. So it efficiently compacts things like numbers like this. So there is a benefit to using this epoch approach. So here's an example of several incoming readings, and you can see that this is an unordered list, and we're doing this because you're just going to be appending constantly for a very long amount of time relative to the amount, especially a lot more writes than there are going to be reads. So this unordered list makes sense, But then things also can come out of order. As an example here, two of these minutes that are in red are coming slightly out of order. And that's okay, because like we said, when we're looking for ranges, it will just in time order them. And this is a snippet from an article that I wrote that is on one of the two Aerospike developer blogs, in this case on Dev, and there's a link there. You can read the full thing. But just for example, leveraging what we know about ordering, we can ask for all the tuples that are between two kind of like endpoint tuples that we're describing here. If I want to get everything between the minute 1463 and 1464 inclusive, then I would do, the left one will have nil, the right one will have infinity, and we get back those two values that as expected. The next one is, again, an example that I brought from a different repo that I used before. And this is just showing you how we can use tuples more as a struct, where each position has a specific meaning, right? That is just another way to model here. And this is an actual list of 100-meter results, 100-meter records, sorry. Now, you can see here that we can have a situation where we want to find everything that is close to a specific point in time rather than a range. And in this case, we want to find, we have one data point and we want to find the range of results that are relative to it. And what we're going to do is we're going to use relative rank range. There is nothing actually, no exact record that has 10.0. But we're going to describe that data point, and you can see how we can now ask for start at the value 1 to the left of it, that -1, and give 2 from there. And that gives us the two that are marked in red. So in this example, we basically have two lists of tuples, and notice that there is actually an overlap between them. And this is going to demonstrate something we can do about that. So let's say we wanted to combine them. We wanted them to be ordered and unique. And so how would we do that with Aerospike? So first thing, we're going to take the first group, and we're going to insert it as an ordered list. Okay, we're going to insert it, and then we're going to declare in the next operation, we're going to set the order to an ordered list. It's just one way to do it of many. And then we're going to combine the next one in, and we're declaring a policy that says, okay, this is going to be unique. We want to not throw an exception if there's a collision. In this case, there will be. And we want to do the best that we can. We're going to do the partial results, the ones that don't violate uniqueness. And we have this operation here that's going to use the policy to insert the second part, the second group of results. Okay, so that's the first thing we're going to do. So let's run this. I'm going to add the first group, and then we're going to add the second group. And you can see now that we managed to do it, and there's only one entry there that was supposed to be the collision, that 992, sorry, the 993, 992 results. The next thing we're going to do is just we're going to ask for by rank range, like we had in the slide before. And we get the two closest to 10.0. Here's an example of a map, just so we can clarify map terms that we're using. So the map key, obviously, is the identifier part of the element, for example, A. The map value is the value part of that element. The key A, the keys A and YY both have a value of 1, for example. The index is the order of the key. Okay, so in Aerospike, there is an index two maps. And in this case, the index of Z is either 4 or -1. You can go forward or backward. The index of A is 0 or -4, and that has to do with insertion order in this case. The rank is the order of the value. Okay, so you, again, can declare maps to be different, of different types. They could be unordered, K-ordered, or KV-ordered. If you're doing rank operations on a KV-ordered map, that's going to be more optimal, but you can still do those operations on a K-ordered or an unordered map. It's just that it's going to take some time, sorting it beforehand. A KV-ordered map is going to have, especially if it's in memory, is going to have an index that allows it to do all kinds of things more efficiently with regards to rank. So this is the map operations API, and you can see that I similarly arranged it like the list operations API into groups. The write operations are on top, the read operations are in the middle, and then there are these remove operations that match. It's very similar to the list operations, except for that here we have index, key, and value. So let's look at map value comparisons. Similar to the list value comparisons, however, these work differently. So the first thing that is being compared is the number of elements. In list, that's opposite. In list, it's the kind of like lower priority thing. Here, the number of elements matters. So a higher number of elements gives you a higher rank, basically, or in the value comparisons. And this is something we're going to take advantage of in an example that I'm going to show you in a bit. Okay, let's skip this. So maps have several advantages over using bins for document modeling. Number one, there is the 32K unique bin names per namespace limit. So if lots of applications are at the same time creating bins and they're not being judicious, you could actually hit this limit. When you're using maps, it's not going to happen because we're not actually counting map keys in any way. There's also a limit of 32K bins per record. There's a performance problem with that. You don't want to have thousands of bins in your record. There's also a lot of metadata overhead associated with those bins. If you use just one map instead, and again, those aren't counted, you can have lots of map keys and it's not going to be a problem of performance. The last thing also is that bin names cannot exceed 15 characters and map keys don't have such a limit. And maps also use the very efficient message pack serialization, so they become very efficient when you're using larger structures. So let's talk about operations on nested elements. Aerospike versions have been adding features that allow you to use document modeling, and it's only gotten easier over time. So the list operations were added in 3.7 quite a long time ago, several years ago. Map operations became GA in 3.10. List and map operations on nested structures were added in 4.6. And we're going to call the nested structures a subcontext. That's the term that we use in our documentation. And then just recently, automatic path creation to a nested sub-element was added in 4.9. This example shows what we've learned in the previous slides. We're going to take 3 credit cards and we're going to embed them inside a user object that has a cards, that is a map. One of those map elements is cards, and the cards is going to be a list of cards. Now we're going to have 3 separate credit cards and select one of them as the default. And I'm going to show you how that works. So let's run this thing. So first thing, we're adding one card, and we're defining, as you can see here, a context for the card for this this map put operation to work on. Okay, so we are creating inside the map. We are creating under user and cards. We are creating an empty list. This has the create only flag and no fail, meaning we're trying to create the path. If it's already there, just skip, don't exit with an exception. And now we're going to add the credit card, and we're going to return the one with the highest rank. I'm going to add a second card and return the one of the highest rank. So what is the highest rank between these two? The difference between map 1 and map 2 is that map 1, the first card, has an extra field called default. And if you remember the ordering, having that extra field, 5 versus 4, is what is going to have it the highest rank. So when we're asking for get by rank here, we are getting the first card rather than the second card. Now we're going to do something more complex where we're defining the context to the default card, we're defining the context to the second card, and we're adding a third card. So what we're going to do here is we're going to append the third card. We're going to go to the context of the default card and remove the default field from there. Then we're going to the context of the second card and set it as the default, and then get by rank. Let's do that. And you can see that now, even though there are 3 cards, because card 2 now has this extra 5th field, it is now the one with the highest rank. Nesting objects as subdocuments is a core denormalization technique. It's useful for data that's often read together in order to reduce drive I/O, CPU, and RAM overhead. If we have the case of a company record and its address, we can nest that because usually those are read together, even though that address might be used by multiple other companies. So if you come from a relational model, you're not going to be able to do this kind of like query to find all the people that are at a specific address. But if you don't care about that anyway, this saves you the call, and this saves you on the RAM overhead for an extra record. This kind of many-to-many relationship is the normalized for performance here. Okay, for space consideration, a map can be used to consolidate many small records into a larger one. This approach mainly answers an operational concern where you're spending 64 bytes of metadata in the primary index for each object. If your objects are 600 bytes or larger, that's not a big overhead. But when you have a lot of tiny objects, 80 bytes or whatever, this becomes a capacity planning concern because you're paying a very big tax on the overhead. Consolidating lots of tiny objects into a larger record using maps with the object ID as the map key reduces disk I/O and saves a lot on memory associated with the index. However, Aerospike All Flash, which is an enterprise feature, is the correct solution instead of doing this technique. The data and the index are both stored on SSD. Memory consumption ends up being extremely low. It only costs an extra read I/O for record metadata from the flash index, from the index on flash, sorry. And then writes do have a higher I/O cost. So let's talk about a denormalization technique that is well known for document modeling, which is the embedded document pattern. It's appropriate when data is fully contained. Relative to relational database, one-to-many relationships between scalar data types should be expressed as a list or map. If you have a many-to-one relationship between a user and cards, for example, and that's because you can't contain things in a row, you can do that in Aerospike. So for example, again, in a relational database, you would model this as a users table and a credit cards table with a foreign key relationship between the credit cards user ID, which is indexed, and the users.id, the primary key of the users table. As just one user holds a credit card, there could be many credit cards for a user. A list of map elements is an appropriate way to model it, a previous code example. If you need to search for a specific card among user objects, you could leverage the immutability of the card details, the fact that they don't change once you create them, and hash each card into a unique UUID. You can create a bin with the list of card UUIDs, and then, in theory, create a secondary index over this list, or alternatively, you can manage your own index, or you can scan for it with a predicate filter. So secondary index and predicate filters can't yet operate at a deeper subcontext, and this is why we need to flow things up. if you want to query these values. You could create a secondary index over card hashes, which is a list of UUID strings. But currently, secondary indexes prevent a namespace from being able to warm start. So that's kind of not ideal. A fix for this, by the way, is planned for a later Aerospike 5 release. So for data that is less latency sensitive, you can just forgo indexing and use a scan with predicate filters. So assume you need to check if a credit card appears in more than one user account for some reason. We're going to use card user set, which is going to be probably in an in-memory namespace with a one-to-one relationship to a record in the user set. The key for the record in card user set is going to be a canonical form of the credit card data. For example, CVV expires last 6 digits and the zip together. That would be the key to that record. Now, the record would have a single bin with a digest of the user record. So the operations would be create. You would try to write it with a create only after a card is successfully added to user. Catch a record that exists, the error code 5. And if this card is already embedded, this means that a card is already embedded in another user record. To check if it exists is very fast. It's just a metadata lookup. To read, the read would return the digest of the user record, and then you can fetch it with a subsequent read operation. Deletes, you can either set it to expire through a TTL that is equivalent to the expiry of the credit card, or you can use explicitly use a durable delete, passively, for example, if you're trying to do a transaction on a card that is expired, you would then do a durable delete. And the advantage here is that secondary indexes have to check every single node. And there's probably only going to be one record associated with this entry. So we're going to query every single node and be fairly inefficient versus the single read here. So now let's talk about normalized modeling approaches. In this case, in order to do one-to-one relationships using implied references. So normalized modeling just means that we are using separate objects instead of embedded objects. And, in this case, we are going to imply the reference between the two objects. We're going to split the objects into an associated record that is going to live in a different set or even a different namespace. And we're going to, the decision behind this a lot of times has to do with the access pattern. If we are very frequently accessing a small portion of the object and most of the object, which is larger, stays put, maybe you want to split them and have that field become a separate object in an in-memory namespace. And the large object just stays on SSD, and it's fairly, it's very slow moving relative to that. So in this example, we're trying to model mobile phone devices, and the mobile phone is going to have all kind of fairly immutable information. The name might change, the model is not going to change, the model number and the serial number are not going to change. You have a user ID, and then you have bytes. And let's say we're counting the data consumption in an 8-byte integer, which is changing rapidly. So the majority of the object isn't moving at all. And the bytes field, however, changes all the time, which means we have to read the entire object. We need to update a small portion of it and save it and persist it a large object back to disk every time we do this. And that could cause hotkey situations, or in general, it's just not efficient for sort of the consumption of resources on the nodes. Now, notice that the digest, is going to be the same, because digest is running set and user key, that pair, through RIPEMD 160. What we're going to do is we're going to put these in two separate namespaces. We have the NS1, which is on SSD. We're creating another namespace, which is in memory. And they both have the same set and the same user key. So they're going to have the exact same digest. And that basically is the way where we link them one-to-one, even without explicitly mentioning a reference. The operational consideration was the one, thinking about the access patterns was the one that suggested there's an advantage to doing this. So this is, the reason we're going to do it. And, we can just deduce the reference. We're either using the digest if we have both of those pieces of metadata the same, but, they can also live in a different set. And if you know the set's name, you know that the user key is going to be the same in this case. If the data in an object grows in discrete ranges, those ranges could be partitioned into discrete records in the same set. I previously mentioned the IoT use case where we had sensor data taking a temperature every minute for a year. And those readings are always in this list of tuples, epoch, minute, and temperature. You would partition the sensor's data into separate record per day. The user key would be, days since epoch and the sensor ID combined. A record is only, appended to during one day and then remains immutable. So we could then basically retrieve data using batch reads over a prospective key range. So this is an example of what these records would look like. If you look at the key portion at the top, we're saying, okay, these are on, NS1, which is on an SSD. The set is called sensor, and the sensor ID is on the right-hand side, and the day, the epoch day, is on the left-hand side. So day 1, sensor 9876, day 2 of sensor 9876, onwards and onwards. These are continuous, so let's assume there is a, even though there don't have to be records in between, and then we have, days 99 and 100, and 100 is the current day. You can see that data is still incoming. So again, the relationship between the objects is implied. We don't need an index. We don't need to do previous or next because we just can deduce the whole key range by name. We're going to use batch reads, and batch reads are very tolerant of missing keys. So again, if we have a sensor that was off for 90 something days, we can still say I want a range of 100 keys, and it'll just come back with 4. We'll have a whole bunch of nulls filling the middle, but we'll be able to iterate and figure out that data. Getting a year's worth of data from one sensor is just 365 keys. Just a list of keys that are declared there. And similarly, getting multiple sensors for a single day is very easy to do. Okay, we have day 1, and we have sensors 1000 through sensor 3999 continuously. Okay, let's show this in practice. Okay, so you can see here that we're going to get the sensor data for one day, one specified day. That comes extremely fast, 1440 data points as expected. The next is asking for a batch read for 4 days. And again, all of those come back extremely easily. So now let's talk about one-to-many relationships and how we would model them. And here we're actually using explicit references. So first thing, let's say we're trying to model, again, a user and his mobile devices. Okay, so the user details, like name, address, my billing account information, my billing history, change extremely slowly compared to mobile device details. Let's say that's an assumption. I don't really work for a telecom company, so let's assume that's the scenario. Maybe I pay my bill once a month, and that's about all that happens on the human side of things. On the device side, we said there might be more information that changes more frequently. So let's keep these, instead of having them as an embedded, using that embedded sub-object pattern that we talked about before in the denormalized way. Now we're going to have these as 2 separate objects. And obviously we have a many-to-one relationship here. So in the device object, which you can see lives in a different set. In this case, I am using set names that are supposed to map to, classes on the application side. So there's a user and there's a device, and we're using the serial number as the user key for the device, and we're using the user ID for the user key for the user object and that we're trying to get to. The device has a device bin, which is a map, and that has the map information. And we added the reference to the user. So if we wanted to get all the devices of a user, that would be easy. We have on the user, we have user.devices, which is a list of IDs, and then we can batch read those. If I wanted to get the user that owns a device, I get to the device, and then I can use the user field of that map in order to find the user again. So this is an explicit reference here. So now let's show how we would do normalized modeling with complex relationships. So if we're trying to model a Reddit-like system that has users, posts, and comments, and we want to have the ability for a user to post, comment, upvote, downvote, and get karma for their posts and comments. And posts have things like static information like the author, but they also have dynamic data like the comments and cumulative votes up or down. Comments also will have an author, and they'll have a post that they're associated with, and you could vote on them. So again, if you have looked at cat photos on Reddit, this would seem fairly familiar. So let's look at the user object. We have here, again, these are all in the SSD namespace, same namespace. Their objects types are separated by set, distinguished by the set. Again, sets don't have a schema, but in this case, they are associated with a specific class at the application side. And we have the user key. So our awesome handle of Don Kongster has a user field, and the user field is a subdocument that is expressed as a map. This user has a name. They have their cake day, like when did they join. They have karma. This user has trophies, which can be expressed as a list of IDs to the trophies. And then there's the posts that the user has made, comments that the user has made as a list of IDs, and upvotes and downvotes. And I'm using a shorthand for UUID. Let's assume that these are all UUIDs, which would be kind of the safest way to do this. On the other side, we have the posts, and a post will have, a title. In this case, you can see that this is a post by Mr. Don Kikong. There's the title. There is the user is set there, so that is a reference back to to the user table. We have the number of votes, which is changing. We have a comment count to just make it easier for the display, even though you could do the size operation, list size operation on comments. We have one field for comments that is just showing, references, the IDs of the comments, and they're just expressed as a bunch of UUIDs, a list of UUIDs. And again, if you think about the size of this, even a really one with a lot of active comments is still going to be just a few tens of Ks, right? Most objects are going to be much smaller, but they have the ability to grow that way. And we have the comments in a tree format, which should allow somebody to kind of like show the nesting of them. And then let's say if you're not posting a URI to something, you can post text in a body. So it's an either or kind of situation. And in this case, our user both posted and commented on their post. So let's look at comment 98209. There is the text of the comment. It shows the post. Again, there's a reference from the comment to the post and a reference to the user that made the comment. When it was posted and votes total. So every upvote gives it a +1, every downvote gives it a -1, and that just shows the value there. Now, we are using either a scalar reference in the case of post.user, or we're using list references if there's a many-to-one relationship. Posts to comments is one-to-many. Users to comments is one-to-many. Users to posts is one-to-many. This is all things that we can express through this modeling approach. Now, the benefit of this is that, there are no complex joins here. If we wanted to load a post and get the post objects to display, we would first load the post itself, and then we would issue a batch read on the comments. And you can see that in action if you go to Reddit, right? Like sometimes the top is going to load separate from the bottom. So again, let's assume that the user side is issuing separate requests for this. So there's a batch read that follows the post itself. The front end can display them in a tree structure the way they want to do it. To load a user's comments, if we have a comments page for that user, we could just go ahead and do, get the comment IDs and do a batch read to get all those comments. To load the user's posts pages, again, we would just load whatever information from the user and then do get the post IDs, create a batch read for the posts. One thing we probably want to do is we want to actually not append the posts and comments, but we want to prepend them so we can do them in display them in order. Like you could do pagination here, right? There's the list operations allow you to say, I want to get an index range. So maybe I want to get the first 20 comments or the first 100 comments. It's not a problem. You can just get those, turn those into a batch read, and go get the comments that you want. So we would actually be inserting them at index 0 rather than appending them. Each time someone upvotes a post, you would also go and update the votes of the page and the author's karma. So you just kind of like tie that together. Each time someone upvotes or downvotes a comment, you also go ahead and update the comment and the author's karma. So these are all operations that you can do separately, like concurrently, basically. Let's talk about, of course, some map gotchas that you should be aware of. First thing is, you've seen how these features have been rolled out in different versions. So you got to make sure that your server and the client versions match the feature that you're trying to use on the application side. Not rocket science, but we've run into that before. The next thing is just a reminder that map order policy is only used once when the map element is created. Even though there's you can pass a map policy for every subsequent operation, it is not going to change just because you gave it a map order policy that is different. In order to change it once it's created, you just need to use the explicit map set type operation. Again, Aerospike transactions allow you to do that. It's just that it's an expensive kind of thing, so we don't try to do it implicit. We want you to make an explicit decision to change the order type. However, the server side, has a check and will not, try to sort something that is already an ordered map, right? If you issue this, again and again and again, and it's already ordered, it'll stay ordered. The next thing I've mentioned before, but it's worth mentioning again, if you are doing data on SSD, K-ordered maps have a significant performance advantage over unordered. And all it costs you is an extra 4 bytes of storage metadata. So really the choice should be between K-ordered and KV ordered. Use KV ordered if you're doing a lot of, by rank operations. Otherwise, just use K-ordered. That's like the most logical thing to do. The last gotcha is basically the fact that if you're using data on SSD, you have a write block size, and at most it could be raised to 8 megabytes. But you're going to get an object too big kind of error if you're trying to write something that is bigger than a write block size, and the biggest you can make it is 8 megabytes, and that's a hard limit. Now, it's also not practical to get to that if you're doing a lot of write operations. If you're doing a lot of reads, not even that many reads, and it's an infrequent update, sure, you can go up to that size, right? If this is archival or whatever statistical information. But if you're doing a lot of operations, I would suggest that you split it according to logical ranges, kind of like we did with a sensor example, where we could have kept accumulating into a single record, but there was no point to that, and we found a way that is much more efficient. Okay, so I wanted to add a section about how we query documents, but before we do that, let's talk about disambiguation of terms. In a relational database, you find data always by a query, right? That's the SQL query language, and you use queries to find anything. Queries use predicates, the where clause in the case of SQL, and this is how we declare the search criteria, right? Like to find the correct records. You have an optimizer in an RDBMS that uses indexes to speed up a query. So there might be indexes there, and the optimizer will use them or use a combination of them based on information that it knows about what is being indexed and the data. Now, sometimes full table scans do happen when the index, the optimizer believes that the indexes won't help. So for example, if it's too unselective, right, meaning too many records are going to come back from the index, it's kind of like, might as well just do a table scan, it'll be faster. Or if the table is too small, it's not worth it doing the lookups in the index, just go ahead and scan. Or a user could give a hint to say, I want to, scan the full table. But a full table scan really is something that kind of like is not super ideal, and it's like a downgraded performance, right? The optimizer will try to use indexes otherwise. Most other databases also use the word query in a similar way. Now in Aerospike, at least as of 4x, there is no optimizer. You need to kind of like hand roll your own optimization. So you need to think in a more procedural way as a developer. So first thing, query in Aerospike means searching for data using a secondary index. That is literally what query means. That means that the index must exist. You can't run a query, an Aerospike query. You can't, do that without the index. A scan means that we're going to access every record in a namespace or a set by walking the primary index. So a reminder, Aerospike always has a primary index, which is going to hold the metadata for every record. Whereas tables in an RDBMS, especially if you're doing something like a data warehouse, your fact table usually doesn't have any indexes, and definitely no primary index. Okay, so both queries and scans, however, could use predicate filters, which are a lot like a where clause. Now, in the case of a query, the query checks a single predicate against a secondary index. You can do very, very simplistic stuff. You can say, I want to do string equals on a secondary index built over a string bin, or I want to do some very simple integer comparisons, less than, greater than, equals, or between. Or I want to do one of two types of GeoJSON operations, which is all the points contained in a polygon, or all the shapes that contain a point. And those could be applied in a query first. They will be applied first, and then any records that we find there could be run through an optional predicate filter. So you would think about this if you're doing something that is a kind of like a SQL query in Aerospike. You would first have to think about which index are going to use if there are secondary indexes, and think kind of like an optimizer. Is this highly selective? Meaning, is it going to toss out a lot of records and leave me a very small set of records to read and apply the predicate filter, the rest of the where clause to? Now, scans also can use predicate filters. It's just kind of like a table scan in an RDBMS, except it's better because it actually uses a primary index. The primary index, again, is like a primary key. If there was a single primary key that was applied to all the tables in a database on the relational side. Also, as of 4.9, scans with the predicate filter or just by themselves can be paginated. So you can walk through and just say, I want 10,000 records, and then give me the next 10,000 starting from the last digest I processed, and you can walk through your data that way. So that's an advantage that scans with predicate filters have. If you're using a secondary index, it's still coming in completely random order, and you don't have a way to really ask for batches of records. Now, again, we could also query inside the document, right? If a document has a lot of data in it, we can query inside of it, finding the elements that we want using list and map API operations. And of course, we can execute those at the correct context. So I gave an example of querying the IoT devices for a day's worth of data, but soon I'm going to give an example of how you query for just a few hours of data from a specific day. Now, using references and batch reads, we can go ahead and fetch all the records in a one-to-many relationship. That's also something that we don't need a SQL type query. So again, when you're coming from a relational database and you think of everything as a SQL statement, a select statement, in Aerospike, most things are key value, or they're batch, of batches of key values, or they're list and map atomic transaction operations for querying inside a record. Because in Aerospike, again, records will contain lots of data because it's not just scalar data. So what would be multiple records in an RDBMS a lot of times will be a single document in Aerospike. So how do we filter for attributes other than an object ID? So again, a predicate filter is something we talked about. It's not just for scans and queries. You can use those also with any type of key value operation. You can attach them to a batch read. You can attach them to a single object, key value operation. And in the previous example, if we wanted to find all the comments that have at least 5 votes, of a post, we could easily do that, right? We would do this batch read, we would get all the comments for the post, we would turn it into a batch read, but we would also add this predicate filter that says, also check that, this value is, at least 5 votes, and that will allow us to basically skip records that don't pass the filter. So back to our example of querying, the IoT data. Basically, we're going to do 2 things here. The first one is to get 2 hours worth of data from December 31st, and we're going to do that with a get by value range. And here it is. And the next one is we're going to use a predicate filter in order to do a digest modulo. We're asking for modulo 120 out of 365. We can expect 3 to 4 records to come back with a predicate filter across the entire set. And that is what we get back. So what are relevant future development? There's going to be future Aerospike 5 releases that are going to continue to add developer features. First thing, predicate filters are going to continue to be expanded, and we're eventually going to add all the missing list and map API operations. Secondary indexes are going to get a full rewrite, which is going to address a few things. One of them is correctness. Scans are already correct, even if the cluster size is changing and data is migrating. Queries are going to get that too. Memory consumption is going to go down. The performance is going to increase. We're going to allow for pagination just like you can do currently on scan. And the last thing is we're aiming for operational ease. We want to make sure that you can also warm start with secondary indexes. So that's a goal for things to come. So what did we skip today? This is a pretty long workshop. First thing, bitwise operations on the bytes data type, blobs, allow you to do different kinds of modeling. Doing things with bit fields instead of maps, for example. I gave a talk at the Aerospike user group meeting in Tel Aviv, I think in December of 2019. And the slide deck for that is up somewhere. You can look at that. I'm also going to follow up with a blog post about it. But that's one thing that can be embedded in a list or map, but you cannot currently do bitwise operations on an embedded data type. So you need to have this in its own bin that has a bytes data type. But again, that's okay. Aerospike records are documents. The next thing is hyperloglog is the first probabilistic data type that we've added. It is actually implemented as a hypermin hash, so it does have min hash capabilities if you want those as well. It's very useful for solving things like the count distinct problem. Lets you, the Aerospike version of hyperloglog allows you to tune the trade-off between precision and storage size. So you can decide how many bits you're going to allocate to the hyperloglog. Now, if you do optionally allocate min hash bits, you'll be able to do min hash type of things, like, for example, intersecting more than 3 sets together. If you have a use for that, you can allocate more space for this extra functionality. Hyperloglogs currently cannot be embedded in lists or maps. They need to live in their own bin. And we have a talk, I think on day 2 by Andre on hyperloglogs, and you really should attend it if you're a developer. Now, I forgot to mention a really detailed explanation about how MessagePack serialization optimizes documents, or how using the compression Enterprise Edition feature works for that. But if you, again, go to the developer blog and read my article about doing user segmentations with maps, that is, I go into quite a bit of detail about it there. So in summary, Aerospike is a distributed database that supports both a key value and a document model kind of approach. You can use familiar document modeling approaches just the same with Aerospike as you would with MongoDB or Couchbase or whatever. Modeling for the access pattern is essential for performance, right? Like, you can't just throw everything in one giant map. You might want to split them and use references or implied references like we talked about. You can use maps with embedded sub-documents to get around all kinds of bin-related limitations, right? Because, again, we're not counting map keys in any way. There is a rich list and map operations API that you should become familiar with, and you now know that it can be applied at any depth using contexts, and the contexts also are, have gotten more expressive over time if you look at 4.9 versus older versions. And the last thing is just reminding you, Aerospike transactions are atomic. You can do multiple operations on a single record in one atomic transaction. It's not something you can do in a standard key value system like Redis or Memcache. In that case, Aerospike is a lot more like an RDBMS or other types of databases which have multiple columns and allow you to do multiple operations in a single transaction. So what should you do next? You should go to other Summit talks in the developer track. For example, the hyperloglog one that I mentioned. Read articles on the Aerospike developer blog. Usually they exist both on Medium or on Dev. If you don't like the paywall on Medium, a lot of the articles are also duplicated into Dev. Go ahead and clone repos in the Aerospike examples org. Run them, read the code, change them, fork, offer pull requests. You should take Aerospike Academy training. If you're an Enterprise Edition customer, likely you have credits. Also, there are ways to get a lot of Aerospike Academy credits so you can do a lot of training for free. And I would subscribe and read the Aerospike stand-up. It comes out every 2 weeks. It's not too frequent, and it really gives you a lot of information about meetups, releases, developer features. So I'd like to get to some of your questions. Let me actually see if I can figure it out the webcam. That would be. All right. So first thing, there's a question about whether there's a penalty on uneven list size. So I'm going to assume that what it's referring to is that if you have different records, with a list data type in them, and a few of them are much larger than the others. There shouldn't be really, except for on the operational side, obviously to read and process a very large object, like let's say you have something that is way outlying, like you can have things that are typically 1K and then you suddenly have a 1 megabyte record. That record is going to take longer to read, process, and send out. But so it itself could be affected in terms of like a hotkey situation on that, right? Because we said when you're doing a transaction, whether it's read or write, you get a record lock and it locks it. These are very shortly held, but they still lock it and other things will pile up behind it. For the reads, if you have an issue and you have a really large object, you can use, and your data is on SSD, you can use, turn on the read page cache and have that cached, have the OS deal with caching it. And that should improve the performance on frequently read objects. On the, for writes, if that object causes problems, then you're probably going to need to think about modeling it by moving it into maybe an in-memory namespace. Or there's other techniques, but it's a little bit outside the scope here. But on a whole, there's no schema, right? So each record kind of knows when you're reading it, it has metadata and data, and the metadata gives information about how big the record is. So there shouldn't really be any penalty for that. It's not like it affects the other records if one of the records has a really big list. Okay, next question is, what can we do if a map has many small items get too big to be stored in a single record? A map that has many, so we're talking about it exceeding the write block size. So first thing, again, you could tie these things, one-to-one, right? We can create a record. Let's say it has a specific key. You can create a key 1, key 2, key 3, key 4, and then just, there's different patterns to this, but you can do something where you show up, you read key 1, and you see that there's actually a flag in there that says, there should be other keys, and then you can follow up with a batch read, where you synthetically create a list of keys, key 2, key 3, key 4, key 5, and you use that to just go batch read those. Or you can even batch read those in advance. Let's say this is a common occurrence and you know that your records kind of spill over. You can go ahead and just do a batch read ahead of time for your key -1, -2, -3, -4, and then if you're getting a bunch of nulls, there's no reason to do another batch read to get the rest. But there are all kinds of ways to kind of like predictively read things and then check on the results. And if the end of it is a null, then you don't need to get another batch out. For example, if you're splitting these in advance. Next, mention the map increments don't work if the path doesn't exist, been taken care of in 4.9. Yeah, so there are new context operators. If you look at, say, the Java API and you look at CTX, the class, you will see that it now has map create key or list create index, I think. And you can use those instead of the regular context, which just kind of like try to walk to the element that you need to, that you want to increment, for example, in this case, an integer. So if you use those, they will, it's kind of like a make dir -p, where it'll just force the path to be created down there. You don't always want to use this. In the credit card example, if I used this approach and I just wanted to change like default 1, I might end up with a list element that is a map that just has default true in it, or default 1, and not anything else. So you don't always want to use this, but it is available now with 4.9. You can just basically choose whether you're a context that walks to a destination down the path, or like actually forces it to be created as you're walking it. What is the optimal record size for performance? Well, that really depends on the storage device, right? Different SSDs have different characteristics. We tend to say that in NVMe context, 128K write block size are optimal. but you really can use the ACT tool to check on your specific device and see what it is. So that really is kind of device specific, and all SSDs are not the same. There's obviously a whole bunch of different technologies under it, and you're going to have to, we might have the information. So if you are a customer, you can talk to us in the support system, and then we'll see if we have that information. And if not, then the ACT tool is out there, and it's not that complicated to use it. I've used it many times before for performance. Let's see.
There are 2 more questions for you if we have time.
Yeah.
Can you build an index on a map key?
Okay, you build an index on a map key. Yeah, currently the secondary indexes can be built on map keys or on map values. But this needs to be a map that is kind of like at the top level. Like it can't be on a map that is nested. We are planning on adding the ability to index a nested map, kind of like a map inside a map inside a map to, once we overhaul the secondary indexes. So that is planned, but currently if you want to do that, you need to bubble it up to kind of like the top level map in the bin. Okay, so wait, I see a few other ones. Is there a restriction on number of secondary indexes that we can create? Yeah, I mean, well, first thing, just logically think about it. In any database, the more secondary indexes you have on the same data, the more you need to kind of like, it impacts writes. So every write, you need to like update indexes. So having multiples of them have a performance impact. There is also a limit. I don't remember what it is. There's a known limitations page on the website. I believe it's 256, but I might be off. Go check that page. But again, I would recommend against creating a huge number of them. You might, again, like we said, there's a combination of secondary index and predicate filters. Just like an optimizer in an RDBMS will decide that it might not use certain indexes, right, if it has certain statistics, or it might decide to just go to do a table scan. You need to think about whether predicate filters by themselves can't do the job, or if you're combining them with an index, then you gotta, in Aerospike currently, you gotta choose which index you want to combine them with. You can only address one of them. Again, this will change in the future, but currently that's how it behaves. So you may not want to create a huge number of indexes if you mostly don't use them in queries. Okay, let's try to go through these really quickly. Is it true that the limit is 256 per namespace? I going to assume that Piyush knows what he's asking. So again, look at the known limitations page. Next, what is the right function to page through a list? Okay, so it depends on, again, are you doing it, do you care to get the things by rank? Do you want to get them by index? So it's very easy to do it by index. Obviously, you can just say, I want to go between two indexes basically and get everything between them, and then you just step forward. You can also do it by rank, right? Like if you're trying to get the data by rank. So that's another thing to consider. I think somebody tell me if I'm out of time here, or do I have a couple more minutes?
Several more open questions. Maybe you can take them to the Slack channel.
Yeah, let's do that. So, by the way, there is the dev section, the developer area in, and if you go to the lobby, you can see that, and I'll be there after the talk to answer more questions. Otherwise, there's also the Slack channel. You can sign up for the Slack channel, and I'll be happy to answer more questions there. There are a bunch that just showed up, but I need to hop off. So thanks for listening. This was a long workshop. Again, read the blog posts. They're pretty cool. And I'll be in the various discussions in Slack and such to answer more questions.